Okay, guys, it's chapter 12, Alkenes and Alkynes. So let's review what alkenes and alkynes are, and then go through the nomenclature, the naming process. Then we'll talk about something new that we haven't really looked at before, which is isomerization, a new kind for us to look at. We haven't seen these before. Then we'll look at reactions, and then a little bit on polymerization, because that might have to do with your labs. Okay, so sorry about going back, but you have to make sure that you're aware of the two different types. And with that same CnH2n, you need more information. Otherwise, you wouldn't be able to tell exactly which molecule it is. That's the definition of an isomer. All right, moving on. So an alkyne is different because these are triple bonds between two carbons rather than double bonds. Acetylene is what's used for welding. They happen to burn with oxygen and produce an enormous amount of heat, enough heat to actually melt steel, which is how the welding process occurs. And alkynes have the general formula of CnH2n minus 2. So C2H2 times 2 minus 2, or C2H2. All right, so that's how general formulas work, and a description of what alkynes are. And of course, shape of anything where you only have two places where electrons can be found is linear, so this is also a two-dimensional molecule. Not z-dimensional, but two-dimensional. Okay. Because we have alkenes and alkynes that are still hydrocarbons, these are nonpolar bonds. And because they're nonpolar, in general, they have physical properties similar to alkanes. They also have low melting points, low boiling points, and they're insoluble in water. But soluble in organic solvents. Organic solvents. Okay. Now, remember what we talked about before about saturated versus unsaturated? If you're saturated with water, that means you're holding the most amount that you can. So would you expect a alkene or an alkyne to be considered saturated or unsaturated? And it's pretty clear that they're unsaturated. Okay. And because there's no other way when drawing condensed structure to show a double bond other than showing both bonds or showing all three bonds, those bonds, the multiple bond, is always shown whenever you're drawing a condensed structure. Cool, moving on. Don't know why that keeps happening, what I'm doing wrong, but we'll figure it out. What about these last two? I see a double bond, right? If you see a double bond, that allows you to know that it's an alkene right away. And there's nothing but single bonds. And if you have nothing but single bonds, then you're going to have an alkane. And what this is really getting you to do is to train yourself to be thinking about and looking for, having your eyes notice those special functional groups. Because what we're going to learn soon enough is that the reactions happen at those functional groups. So that's the important part of any molecule to be noticing. Okay, let's move on. Now we're going to nomenclature, naming. Okay, so there's a set of rules for naming. And the first rule is almost always the same, which is finding that longest continuous carbon chain so that you can name the parent. Whenever you have that parent, you know that the end is going to have an -ene for the double bond and an -ine if it's a triple bond. So you know the parent by counting the continuous carbon chain that contains both atoms of the bond. That's the multiple bond. And then you get the parent. And then there's the numbering priorities. Number the carbons in the chain so that the multiple bond gets the lowest possible numbering. And if it's equal, then you want the first branch to have the lowest number. Okay, so whenever you gather all that information to finish out the name, you indicate the position of the multiple bond by giving the number of the first multiple bonded carbon. That's where the double bond part starts. And after all, if it's an alkene or an alkyne, that's the most important part of that molecule. So you're going to mention that and let whoever it is that's thinking about your molecule know where the double bond starts. And if you have more than one multiple bond, it's a diene or a triene or a tetraene, or however it is that describes the actual molecule and the number of bonds. Cool. Continuing, let's go through the process of a couple of practice problems. So we've got A and B, two different molecules, one an alkene and the other an alkyne, and let's do our process. So the first thing is we've got to find the longest chain that contains both of the double or triple bonds in the chain. You would never have a chain where you would start like, let's pretend that this is a big long chain here. You would never count 1, 2, well, I guess you would. If the chain was off a different atom, you couldn't make the chain go off and not include both atoms that are bonded by the multiple bond. That's what this is trying to say. So let's see. So 1, 2, 3, 4. So this is going to be a bu or a bute, and because it's a double bond, it's going to be a butene. And this is 1, 2, 3, 4, 5, 6. So that's going to be a hex, and because it's a triple bond, it's a hexyne. So that's the parent. That's how we find that part. 4 carbons, butane gets switched to butene. 6 carbons, hexane gets changed to hexyne. Excellent. All right, now we're going to do some numbering. So we can either go 1, 2, 3, 4, or we could go 1, 2, 3, 4. Which one do you think should be? The multiple bond with the lowest number clearly is going to be this. And because of that, the 1 starts over here. 2, 3, 4, 5, 6. Good, and now you're going to name the compound using the first number assigned to the multiple bond. Let's see if it adds them in. I forget. Yep, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So this is going to be, because the second carbon is the one where the multiple bond starts, we're going to call this a 2-hexyne. And because the 1 is where the multiple bond starts on this, this is a 1-butene. Let's see if we're right. Look at that, 1-butene, 2-hexyne. Nice. All right, so we've got the parent, and we've identified which carbon has the multiple bonds. So the last thing is to name the substituents off the chain. Number and name the substituents. Since we decided that that was 1, 2, 3, this is also 3, and that's a methyl group. Since this was carbon 1, 2, 3, 4, and that's 4-ethyl, right? Okay, so there's only one substituent, so we just tack those on. Methyl group at carbon 3, ethyl group at carbon 4. So we stick those on, and then we write in what we had before. So 3-methyl, then 1-butene, and 4-ethyl, 2-hexyne. Not too bad. All right, so let's try a couple more. First step, longest continuous chain that contains the multiple bond. And we're going to be for sure to try to make the multiple bond a smallest number. So clearly we're starting over here. 1, 2, 3, 4, 5, 6. So that's a 2-hexene, and the chloro is on carbon 5, so 5-chloro, 2-hexene. Boy, that's not too bad. 1, 2, 3, 4, 5, 6. I know it sort of feels weird in this part with how the triple bond goes, but remember, that's a carbon at the end of the carbon-carbon triple bond. So since there's 6 and there's no constituents, we're going to call this 1-hexyne, and that's it. Okay, 1, 2, 3, 4, 5, 6, 7. So it's a 2-heptyne, right? Because it's a triple bond. And that's a 4-methyl hanging off of the 4th carbon. So 4-methyl, 2-heptyne. Not too shabby, not too bad, pretty quick stuff. I guess my pen strength is stronger than I believe. So let's run this through again real fast. 3-methyl, 3-hexene. 1, 2, 3, 4, 5, 6. 1, 2, 3, 3. All right, so that's the formula. The line structure. We start with a CH3, then a CH2. Then a carbon has a methyl group hanging off of it. Then it does its double bond thing to a carbon that has to have an H so that it ends up with a total of 4 bonds. Then you have another CH2, and then you finish out with the CH3. 1, 2, 3, 4, 5, 6 carbons. Methyl on 3, double bond starts on carbon 3. Okay, that's how you have to go about your business. See if you can do them with the practice problems. Okay, one of the things that we also like to do with practice problems is we give you a formula and you pick out the right name, or we give you a name and you pick out the right formula. So how would you go about your business here? Well, start your counting. and start your counting so that the double bond starts with the smallest number. I think it's pretty clear that it would start here. So you can go 1, 2, 3, 4, 5. You could also go 4, 5, right? 4, 5. So how would you decide which one is better? I don't think there's any number that's going to be any bigger than 5. So what that means, it's going to be a pentene, right? It's got to be a pentene. So that means you can eliminate the butene and the hexene. Second, you know that you're going to want to do this so that the smallest number is indicating the double bond. So that means you can eliminate the 3-pentene. So it's between 2-pentene and 2-pentene. So then how do you decide? And remember, if there's like a match and you could go either way, you want to have the most substituents. You want to have the most things hanging off the molecule, the chain part of the molecule. So if you went down here, then you would have 1, 2 substituents hanging off. But if you went here, then you could have 1, 2, 3 things hanging off it. And blue is where we want to go because there's 3 substituents. And you would have 2-methyl, 3-ethyl, 4-methyl, right? And 2-methyl, 4-methyl means 2,4-dimethyl. And what comes first? Eth comes before meth, not the di, but the meth. And so that's why 3-ethyl, 2,4-dimethyl, 2-pentene is the right answer here. Excellent. Practice, 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 practice. You cannot get good at this until you make a bunch of silly mistakes in your practice. What would you rather do? Make your silly mistakes in practice so that you can get better? Or miss the foul shots with the game on the line? Nah, man, you got to practice. How do you get better? Practice. Anybody who doesn't know who Allen Iverson is, look it up. Allen Iverson. Practice. Although he was making a joke about practice because he didn't think he had to show up for practice. But I like to think about practice as the thing that separates an Allen Iverson from somebody who never made it to the NBA. So anyway, practice. These aren't that bad, but a little bit more with the Alkene and Alkyne nomenclature, and this is for compounds with multiple bonds. Compounds with 2 double bonds are called dienes, right? Because they're more than one ene and more than one double bond. And you name these guys by changing the ane to a diene. Each double bond gets its own number, and you want to try to do the numbering so that the smallest numbers end up, right? And if you have a compound with 3 double bonds, they're not dienes, but trienes. And compounds with 2 triple bonds, these are called dienes. Okay, so I think that's pretty clear and straightforward. You'll have some practice for those. Dienes, trienes, dienes, they're not really all that common. So we probably won't spend a whole lot of time on those, but it's still important to be able to see them, recognize them, and name them right. A little bit of practice. So there's pentane, 1, 2, 3, 4, 5. So whenever we're looking at 1, 2, 3, 4, 5, and notice that you wouldn't start the numbering here because you'd rather have the numbering be 1, 3 than 4, 2. 1, 3 is better, and that's why this is 1, 3 pentadiene, because that lets you know that the double bond starts on carbon 1, and then it also starts the other one on carbon 3. Pretty straightforward. Yikes, oh my gosh, that's insane, and it looks like it should be crawling somewhere. Nah, no big deal. Really, really no big deal. You just go through your process. And the first thing to do is start thinking about functional groups. And you've got 2 double bonds. Therefore, it's going to be a diene, right? And since you want the numbering to start with the lowest, of course you're going to start the numbering here. Then there's carbon 2, 3, 4, 5, 6, 7. I think it's clear that you're not going to go in any other direction. So if it's 7 and you've got the double bond starting at 1 and at 4, for sure it's going to be a 1, 4 heptadiene. Right? That's the parent and letting you know that's a comma where the double bonds go. After that, you just start ticking off the substituents. You've got 3, 3 dimethyl. You've got 4 isopropyl, and you've got 7 bromo. Okay, so those are the substituents. So now you have to decide the order in which you put them in, and it's alphabetical. And since isopropyl is special, the iso counts. The I counts in isopropyl. Okay, so that means 7 bromo, 4 isopropyl, then 3, 3 dimethyl, 1, 4 heptadiene. 7 bromo, 4 isopropyl, 3, 3 dimethyl, 1, 4 heptadiene. I know it's a big mouthful, but whenever you go backwards, and this is probably what you should always do if you have time on tests, and I'm always going to try to give you as much time as I can on tests. Did anybody run out of time on quiz 1? No, you didn't. Of course you didn't. So if you're sure and you don't want to give away a point without checking, and you believe that this is the name of that substance, well, why wouldn't you then take the name and draw the substance from it? Because if you messed something up, maybe you would catch it that way, right? So 1, 4 heptadiene means 1, 2, 3, 4, 5, 6, 7. 1, 4 means a double bond on carbon 1, 2, 3, 4. Remember, the 4 means it starts on carbon 4. 1, 2, 3, 4. And then you've got 3, 3 dimethyl. So that means 2 off of carbon 3. 4 isopropyl. There's carbon 4. 1, That's isopropyl, and then a bromo off the end. Look, it's the same. It's the same. It's always worth it to try it. Okay. Now let's talk about the nomenclature of cycloalkenes. Don't forget that 1, 2, 3, 4, 5, 6, that this is not a cyclotriene. This is aromatic. It's a whole different functional group. That's how special it is. And so we never think of anything with a ring with 3 double bonds in it to be anything other than a cycloalkene, or aromatic versus a cycloalkene. Okay, so let's just take a look and see how it goes with these. The naming is the same as with cycloalkanes, with the exception that you always identify the carbon where the double bond starts as being 1, and that the second carbon, the way the numbering goes, always has to go through the double bond. So you would never go 1, 6, even though the substituent is a smaller number, because whenever you have the double bond, it's always going to have numbers 1 and 2. And of course, you wouldn't want to go 1, 2, 3, 4, 5, 6. It's much easier to go 1, 2, 3. So that's why this stuff is called, well, what do you think? What do you think it's called? Three methyl cyclohexene. And you don't need to say the 1 because we know it has to be carbon 1. Continuing on with nomenclature of alkenes and alkynes, when we're talking about cycloalkenes, remember that double bond is always between 1 and 2. The 1, you don't have to write it because it always starts at 1. The first substituent has to be the lowest number after this part comes true. So when we're looking at this guy, your job is to figure out where the numbering starts. Let's see what it has for us. There's the double bond, right? So which carbon is carbon 1? Is it 1 and 2? Or is it 1 and 2? What do you think? Which one will make the numbering of the constituent lower? It's that guy, right? 1, then 2. So what's the name? Well, it's a cyclopentene with a 1-methyl. 1-methyl cyclopentene. Here's another good example. That's a cyclohexene. Where do we make the numbering start? Well, it's either 1, 2, or it's 1, 2. Which do you think? Well, the total numbers, if I went that way, would be smaller, right? You'd say 2,3-dimethyl-hexene. But remember, the ring is numbered to give the first substituent the lowest number. So it's not this, it's this. And so we're going to zip the whole way around and make this 1,6-dimethyl cyclohexene. 1,6-dimethyl cyclohexene. Because if we went the other way, this would be 2, 3. And of course, 2 plus 3 is smaller than 1 plus 6, but that's not the issue. That's not how we name. First substituent has to get the lowest number. Just follow the rules. Cyclopentene. Okay, so how do we do our counting? We could go 1, 2, 3, 4, 5, with bromo at 3 and chloro at 5. Or, let's try a different color. What color do we want? How about back to purple? Or we could go 1, 2, 3, 4, 5 with the chloro at 3 and the bromo at 5. So how do you want to do that? Well, we want to do blue because we want bromo to be the lower number. So we're going to say 3 bromo, 5 chloro, cyclopentene. Very nice. That's what we're looking at. Practice. Did I mention the practice on the other hand? Which practice? One of these? Alan Iverson and practice is practice. Okay, practice. Cyclo. That's how you get better. So get at it. So, in my book, to be quick about this, let's just pretend that this is like lightning round and you get more points for getting it right, like you're taking trivia down at BW3. All right, so first thing I'm thinking is cyclopentene, which means that's out, right? It's got to be out because that's not a cyclopentene. The rest of them are 5 carbon rings with 1 double bond, and that's good. So if it's 4-methyl, what does that mean? That means if we started the counting here, we'd say 1, 2, 3. Isn't that 3-methyl? But if we counted 1, 2, 3, 4, that's 4-methyl. And if we counted 1, 2, this is 1-methyl. That's another good thing to do, is to go ahead and if you had unlimited time, you could name them all and then circle the one that it has to be. And of course it has to be B. Nice. Moving on. So naming is a big old pain in the butt, right? Well, systematic nomenclature is a major thing, especially when we start to deal with some monster molecule like this. Now, granted, butane fuel is easy, but butane isn't the same as diesel or isn't the same as octane or propane. You would not want to stick butane in your grill. Okay, it's not good for the grill. It doesn't make the right kind of fuel, different amount of heat, and it's not going to be a good experience for you. It would be really pretty bad. And as far as, giving a little easier name, it's a whole lot better than that craziness there. But that is specific to that. And you don't want something that isn't penicillin if you need to get penicillin. So naming is critical. That's why we are so careful about it and why IUPAC put together a systematic way of naming so that everybody named it the same. As we move forward in this class, you will see that there's lots of names that people used that before IUPAC came into being, and they just sort of said, well, let's just call it this, and it ends up being confusing, and that's why there's a straightforward name for things. All right, so that's important, and because you're going to get lots of problems on it on tests, that means you better be on it. You better be good at the naming part. Okay, moving on. something that we talked about a while ago with free rotation around single bonds and things like that. We want to talk about the difference between conformational isomers, constitutional versus structure. And the whole key to this is that different connectivity is a structural isomer. How they are different is how they are put together. If you stuck an arm onto a skeleton and then you stuck the other arm onto the end of that arm, that's a different connection than if you put the arm on one end in the shoulder socket and the other arm on the other end of the other shoulder socket. Even though you'd have the same two arms per one body, they're put together differently. Okay, don't you agree, Abby? I think you do. So that's what we remember from isomers, molecules having the same molecular formula but with a different arrangement of atoms. And I hope you recognize that 1, 2, 3 carbons in a straight chain, 1, 2, 3 carbons in a straight chain. This is exactly the same molecule, just with free rotation around this carbon-carbon single bonds. But when we have double bonds, or triple bonds, there is no free rotation around carbon-carbon double bonds. There is no rotation or restricted rotation around the carbon atoms in the double bond. It's much more rigid and they basically stay in place. As a result, 2-butene can be written with two different conformations. One is with the methyl groups both sort of pointing up, and one is with one of the methyl groups pointing up and the other one pointing down, because you cannot freely rotate around the carbon-carbon double bond. So if they're on the same, then that's cis, okay? But if they're trans, like the transcontinental railroad went across the continent, right? From one side to the next. So trans is sort of like trains across. So if the cis is on the same side, cis same, then trans is on the opposite side. Got it? So the cis isomer has the two substituents closest to each other across whenever looking at the carbon-carbon double bond, and then the trans is across from each other, okay? So whenever there are two groups on each end of a carbon-carbon double bond, whenever they are different, the two different groups, on each end, then two isomers are possible. If A is different than B and C is different than D, then you can have the A close to the D, or across from the D, or you can have the A close to the D. Okay? But when two groups on one end of the double bond are identical, they're both H's, or they're both CH3s, or they're both, in this example, it would be A, C, double bond to C, C, D. If it was like that, okay, then you wouldn't have cis-trans isomers, because what's the difference between this molecule and this molecule? Nothing. Just flip it over. If you flip over, it's the same. So take like flipping an egg. If you flip it over from this side over to that side, it looks exactly like that. And so when that's true, cis-trans isomerization is not possible. And this becomes really important. We're going to give you lots of biological reasons why this is super, super important. But for now, we're just going to be able to hopefully look and identify whenever you see them. 4 different spots here. These guys they're both 2 butenes, right? Double bonds on the second carbon, but they're definitely different from each other because you can't freely rotate around that double bond. So cis-butene and trans-butene are considered stereoisomers because the only thing that's different is how they look, not how they're put together in terms of structural, where the double bonds are and things like that. It's just only whether or not the methyl group are across from each other or right next to each other in relationship to the carbon-carbon double bonds. Okay, so that's how you identify cis-trans stereoisomerism versus constitutional isomerism. It's important. Okay. You got to have different groups attached to the double bond. So this is a different group attached to this carbon and a different group attached to the carbon. If you have the same group attached to the same carbon, even with the double bond, there's no cis-trans isomerization. So this is the cis because they're on the same side, and trans means they're across. Okay? And cis 1,2-dibromoethane and trans 1,2-dibromoethane are very different molecules because they're across. Or they're next to, depends on where those bromines are attached. We don't have that with alkanes because there's free flipping rotation around the carbon-carbon single bonds. Cool. Daggone it! This keeps happening to me. I don't know why. All right, so let's do this again real fast. So CH3, CH2, C double bond C. CH2, CH2, 1, 2, 3, 4, 5, 6, 7, 8. That's 3-octene, but we have to think about what makes these 2 carbons happy with the double bond in between them. Needs another H. That's an ethyl group and a hydrogen. That's a 1, 2, 3, if you want to think of it that way, that's a 1, 2, 3, 4. So that's sort of like a butyl group and a hydrogen. Can you see that we could also write this molecule like this? CH3, CH2, CH double bond CH, CH2, 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 CH3. Here, the H's are cis. Here, the H's are trans. Here, because there's no free rotation around this carbon-carbon double bond, the H's are closest to each other. Here, the H's are across from each other. So 3-octene is the only one out of these 4 that has cis-trans isomerization. That's why drawing this out is very helpful, because why we asked you to make sure you included the right number of hydrogens on every carbon in a line structure, because that's the only way you're going to be able to recognize the cis-trans stereoisomers here. Okay? Good. Try to practice on that because it's easy to skip them. Next, lycopene, the red pigment in both tomatoes and watermelon. Can you imagine that the red in the tomato and the red in the watermelon come from the same stuff? Has 13 double bonds in it. And any kind of deeply colored vegetable, carrots and tomatoes and sweet potatoes, anything that is highly colored is good to eat because it's an antioxidant. Prevents unwanted oxidation from occurring in your body. Oxidation occurring in your body is basically aging or taking out cells that you don't want to be taken out. So eating that stuff is good. That's what lycopene is. Look at all those double bonds. So that's why you want to eat that stuff. There's other interesting alkenes and alkynes that we deal with all the time. When we're dealing with birth control, these two, estradiol and progesterone, are the female sex hormones. And whenever you make molecules that synthetically want to look like estradiol and progesterone but aren't the same, what do? Well, you make as much of the molecule similar as you can, but then maybe it's easier or not as difficult if you have something attached that's slightly different. And so that stuff or that stuff act just like that stuff and that stuff. So you're able to mass manufacture these materials as opposed to try to extract these natural products. And so that's how we can get lots of synthetic birth control pills out there for people who need to use them. Tamoxifen is a breast cancer chemotherapy for those breast cancers that want to grab estrogen. And you can see that carbon double bond. And I hope you can see that since this and this are different, that we could also have cis-trans isomerization here, right? Because we could also have the phenyl groups next to each other, and then these sort of alkyl parts next to each other. So that would become really important because it might be that this trans version works, but the cis version may not work, or it may be really hard to make or something like that. So it's really, really important to be able to stay on top of that. Okay, so we've got the naming and we've identified isomerization, and we also now have to talk about reactions. And the key to this is that organic chemists look at reactions very differently than the way you've been looking at reactions all along. In the past, we'd say this stuff reacts with this stuff to make this new stuff, and that would be it. You'd try to balance things, and then you'd look at multiple ratios and figure out how much you started with and how much you could make and all the rest. But in organic chemistry, we identify and examine the molecules. We look at them special to try to determine where the reaction occurs so that we can predict what particular thing gets made, not just how many of each atom, but the molecules are different. After all, we can even make cis-trans isomers that are very different from each other. How does that get done? Well, you have to look at the reactions in a different way. So this same reaction here, remember, C6H12, so what might we consider that to be? What kind of molecule would you expect that to be? Well, it's CnH2n, so we might think this is either a cyclohexane or a hexene. And since we're in alkenes, alkynes, it's pretty clear that it's a alkene. So now we're looking at this stuff and it's reacting with this. And we have to decide, this is your job as an organic chemist, which is basically what we're training you to become, is to look at these and say, what kind of reaction is going to occur? It's the connectivity and arrangement and sometimes the stereochemistry of the molecules that's important. And what we end up finding is this is the material that gets made. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens, 1 bromine, 1, 2, 3, 4, 5, 6 carbons. That's what that stuff is. Okay, so how did it get there? How do we know? How do we predict? That's our job. Let's see what the job feels like. So we're reacting alkenes. How do they react? Remember when we looked at alkanes, we said that they don't react very much. About the only thing that they can do really is be combusted, burned, reacted with oxygen gas to make carbon dioxide and water, basically sort of blow up the whole molecule in a way. But here, alkenes and alkynes, they do different things. They undergo what are known as addition reactions. And where do they add? They add at the double bond. They add at the functional group. Okay, so addition reactions basically add X and Y to the alkene at the double bonds. One bond of the double bond is broken and 2 new single bonds get formed. So we add on X here and Y here. The double bond is gone and 2 single bonds get made. Don't forget, hydrogenation and hydration are different. Remember, hydration is to get hydrated. Add water, which is different than hydrogenation, in which you add hydrogen, or halogenation, in which you add a halogen, or hydrohalogenation, in which you add a hydro and a halogen. Okay, so let's go through these guys and try to look at the reactions and predict. Okay, addition reactions. The first one we'll look at is hydrogenation. Hydrogen. So we're adding H2. So we add H2 to a multiple bond. You usually need a metal catalyst, like platinum, or I'm sorry, that's palladium, platinum, ruthenium, and nickel. So anytime you see one of those, they are catalysts that help this happen faster. And what you do is you turn an alkene into an alkane. Now, if alkene, would you consider this to be saturated or unsaturated? Would the alkane be saturated or unsaturated? It's important to remember that alkanes are saturated. All single bonds. Good? Good. Now, we talked about these metals being catalyst. What is a catalyst? Catalyst is something that accelerates a reaction, makes it go faster, because there's an energy barrier that you have to get over before you can get the reaction to occur, okay? And without a catalyst, it takes more energy, it's tougher to get over top. Whereas whenever you have the catalyst, it's easier to get over that, what's known as an activation barrier, to then start down to make the products that you want. Notice that the overall energy change, that's what enthalpy is, it doesn't change, nor does it change the reaction itself. All the catalyst does is make it easier. And the catalyst is recovered unchanged. Think about it. Think about the catalytic converter in your car. Does that run out? Does that like get used up and makes other stuff, and every so often you have to drive to the gas station or to the catalytic converter station and get an extra fill up on your catalytic converter? Nope, never happens. Why is that? Because the catalytic converter does a good job of converting the incomplete combustion gases that get formed in your combustion engine whenever the fuel reacts with oxygen gas to make carbon dioxide and water. Well, it makes other stuff too. And what the catalytic converter does is it allows the car to take those other compounds and further react them. And it takes a little catalyst to make that happen faster and quicker, to make more product and less dangerous stuff like nitrous oxides and carbon monoxide and all the things that cause smog to occur. And with the catalytic converter, that doesn't happen as much. But nothing ever changes in the catalytic converter. The reaction keeps occurring and the catalysts that are in there stay the same. That's how the catalyst works. It's interesting stuff, but we're not going to talk about it in Chem 112 on the how that works. Just so that you know what that catalyst means. Okay. I do. Okay, so if we're going to add H here and H here, what do we make? CH3, CHH, single bond with CH with another H, and then a CH3. Well, CH with an H and CH with an H is just CH2, CH2. So that's it. You're just going to make butane. The H jumps on here, and you're just going to make with 2 hydrogens attached in every spot. Before, you only had 1 hydrogen attached and 1 hydrogen attached in those carbons that were involved with the double bond. Now we're going to add that hydrogen and that hydrogen onto this carbon and this carbon on the double bond. And what do you make? You just make cyclopentane. If we're going to add the hydrogen here and here, what are you going to make? CH3, CH2, CH2, CH3. Butane. Good job. Okay, so that's hydrogenation. Halogenation takes a halogen and adds on top. So halogenation adds an X and an X, with X being either chlorine, bromine, or iodine. This is easy to do. You don't need to try to hurry the reaction up. It happens simple. And it's called a dihalide, or a synonym for it is a dihaloalkane, because the double bond is gone. The second bond between the carbon and the carbon, it's not a carbon-carbon double bond anymore, it's a carbon-carbon single bond. It's considered saturated because there's no multiple bonds. Even though they're not all hydrogens, the fact that all the carbons are single bonds means it's considered to be a saturated product. Let's take a look at what that might look like. I was wrong. Okay, so the chlorine comes in here, the chlorine comes in here, and what are you going to make? CHCl and Cl. Notice that it's saturated, no double bonds. What about this guy? We drew in on this cyclohexene, the hydrogens. The Br comes along, reacts in that carbon and the other one in that carbon. The double bond goes away. The ring stays there. The hydrogens stay there. But now you've got bromines attached at carbon 1 and carbon 2. 1,2-dibromo cyclohexane. 1,2-dichloroethane. Cool. Okay. So what do you think? Man, this is organic chemistry at its most simple and most repeatable. Here's a starting product. Here's a substance that you're going to use to react. Your job is to predict the product. That is not a simple deal because you have to identify what the interesting reactive part to the starting material is. You have to be able to analyze what the reagent is, the stuff that does the reacting, change that initial reactant, and you have to be able to figure out what it does, how it does it, and what the product is. But this one isn't so bad, right? You're going to add an iodine onto each carbon. The ring structure stays the same. You have a methyl off of this guy, and so you're going to have an iodine off of there and an iodine off of there. So which one is that? Oh yeah, let's see. So what's that called? Where do we do our counting? Well, we want our number to be the smallest numbers possible. So we're going to say 1, 2. So this is a cyclohexane. Right? And what do we have on each? Well, I comes before M because that's a methyl. Yes. Okay, so it's 1, 2, diiodo, 1 methyl. Cyclohexane. 1,2-diodo, 1 methyl cyclohexane. Excellent, excellent. Moving on. This is one of the labs that you would be doing if you were in the lab, doing the lab, but I don't think you're able to have bromine at home. So you might see an example of this. You might see a video of it. Dr. Perrone will be going through this process, but you're going to have to be able to identify and recognize how this works. And it's pretty clear that when you have an alkane, it doesn't like to react because it doesn't have no functional group, no place for no functional group to react. So it just sits there. But if you have an alkene, you have whatever's out there and whatever's out there, and you're going to have an addition reaction where it's now a single bond. Bromine is red, and if it disappears, that means it reacted. It's sort of cool. It's obvious that a reaction has to have occurred, and you know, therefore, whether or not your initial clear liquid that you wouldn't be able to tell what it is just by looking at it, whether or not it's an alkane or an alkene. It's nice. It's cool. It's chemistry reactions, organic chemistry reactions in action. More alkene reactions, hydrohalogenation. So hydro is H, halogen is an X, so it's an HX molecule, either HCl, HI, or HBr. Hydrohalogenation. That's adding HX. And it's the same sort of thing. You add an H onto one of the carbons of the double bond and an X, whatever, either it's chlorine, bromine, or iodine, and the HCl, HBr, or HI onto the other. You make the carbon-carbon single bond, and you make an alkyl halide. Again, this is simple, so you don't need to do anything extra to force or make sure the reaction can happen. It's easily done. The product is an alkyl halide, meaning just a halide. Sorry about that. So basically it's just an alkane with a halogen substituted off it. And again, saturated. No double bonds. All single bonds. Cool? Cool. Okay, so now let's do some examples with symmetrical alkenes. And you'll see what we mean by symmetrical in just a second. So the HCl adds by sticking an H here and the Cl here. Now, why is it symmetrical? Because that side looks exactly the same as that side. That's the symmetrical part. You could basically make a mirror, and that side looks the same as that side. So that's symmetry. And if you think, well, what if I did the Cl first and the H second? Well, just look at that exact same molecule from the other side. Like if you walked, like you're looking at it this way, well, what if you walked around and looked at it from the other side of the molecule? It would look the same. H on the second carbon, Cl on the third carbon. If you walk around to the other side and look at it, H on the second carbon, Cl on the third carbon, it's the same. Or if you took the molecule and you flipped it over. So there's nothing different between the two. The mirror is right here, and H and Br is the same as BRH. It's the same. If you just rotated the molecule, flipped it, it would be the same. Mirror plane, so it's symmetrical. Mirror plane, so it's symmetrical. So it doesn't matter. If it's symmetrical, you're going to make the same thing every time. H comes on there, Cl comes on there, and you're going to make H, 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 Cl. Besides, it's single bond, so you get free rotation around everything anyway. Same deal here. You're going to stick an H there, Br there, the double bond goes away. That's it. Bromocyclohexane. Good. Okay. So those are symmetrical alkenes, and those are simple. But this is where we start to get a little bit more interesting and a little bit more complicated, and that's with unsymmetrical or asymmetrical alkenes. When the alkene is not symmetrical, you can make two possible products. Now this is symmetrical, right? You can see that, right? On this side, looks exactly the same as that side. So you could add that hydrogen here, or you can add the hydrogen to carbon 1 or to carbon 2, right? But this molecule and this molecule are identical. Right? If all you do is flip it over, you got CH3, a bromine on carbon 2, a hydrogen on carbon 3, and then a CH3. If you counted the opposite way, bromine on carbon 2, hydrogen on carbon 3. So they're the same. But what about an asymmetrical alkene? If you're an asymmetrical, you got a methyl group here, and then you've got an ethyl group here. So the H could be adding to the carbon that has a methyl group attached to it, or the H could be adding to the carbon with an ethyl group attached to it. And this are not identical. They're different molecules entirely. How do you know they're different molecules? How would you name them? How would you name this? You'd count the smallest number of carbons, or you'd count the number of carbons in the parent with the substituent, the smallest number. Isn't that 1, 2, 3, 4? So that's 2 bromobutane. What if it looked like this? Wouldn't you start the counting from here? 1, 2, 3, 4, 2 bromobutane. They're both the same. Are these the same? Would you name this and this the same? Well, if you counted the longest continuous chain, it's 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5. So both of these are pentanes, right? So pentane, pentane. And they're bromopentanes. But remember, for every time you name, you have to put the substituent on the smallest number possible. Isn't this one 2 bromopentane because it's on carbon 2? Isn't this one on carbon number 3? Hey, bromopentane, 2 bromopentane is not the same as 3 bromopentane. So 2 possible products can be formed here. I think that's pretty interesting. And you got to be careful. And you got to figure out which one is which. And that's the big question. Which one of these has priority? If you can make both, is it half of one, half of the other? Is there one that's more easily made than the other? Let's find out. Well, guess who looked at it? Oh, I'm going to talk about this first. This is basically what we were just discussing. And I think it's clear that we've got 1, 2, 3, 4, 5 versus 1, 2, 3, 4, 5. So because they're connected in different ways, this is like sort of putting the thumb on the end of your hand or putting your thumb where your middle finger is. Hey, you still have 4 fingers and a thumb on your hand, but they're not the same. And because they're not the same, because they're not the same thing, these are constitutional isomers. These wouldn't be stereoisomers. There's no double bond, right? No double bond. Are they isomers? Sure. Count up the number of carbons, hydrogens, and bromines. They're the same. So the question is whether it's a conformational or constitutional isomer. Conformational would be just how they're, stuck together, or how you would draw it. Whether you would make this look like this on that side, or make it look like this off of carbon 3. Right? Those are conformationals. No, this is actually constituted differently. So those are constitutional isomers. 2 different names, 2 different materials. So who studied this first and was careful about figuring out how to deal with it? A dude from Russia named Markovnikov. And what did Markovnikov find? He found that the H atom in the hydrohalogen will bond to the less substituted C atom in the CC double bond. What does less substituted C atom in the CC double bond mean? Basically what we're talking about here is that H adds to the carbon in the double bond with the most H's already attached. Okay? So there's 2 ways of thinking about this as a way to remember it. One is that the rich get richer. Right? That's the trickle-down economic theory doesn't really work in my experience. And so what that means is the rich get richer and the poor get poorer, which means that H's go with more H's. Not go with, how about add to? If we want to think about like dissolves like, we can also say that like gathers with like. Okay, so the whole idea here is that if you had to decide which carbon in the carbon-carbon double bond gets the H and which one gets the X. The H is going to go to whichever carbon has more H's already attached. That's how it works. That's what Markovnikov found out. And he did so many reactions and isolated the products and recognized that they were different. And he was the first guy to publish this. And so he did so much great work that it's basically a rule that everybody knows, Markovnikov. So if you were going to look at propene, remember H is on this side, a methyl and an H, so this is an asymmetric alkene. And only have to worry about it with asymmetric alkenes. The H could go on carbon 1, or the H could go on carbon 2. Which one? Well, if the H goes on carbon 1, I guess I'm mixing up the numbers. That's my bad, because it should be 1, 2, 3. So notice that the H likes to go onto the carbon that has 2 hydrogens on it, whereas the Cl is going to want to go on the carbon that only has 1 H on it. If we did it the other way around, notice that the H is going on the, right, this is from the double bond that only had 1 H, whereas here, this guy has 2 H's. So this is the Markovnikov rule is telling you that this is the major product. Now there are reasons for this. They're known as mechanisms, and we can look and think about where things leave and where things go in and why they want to add this way. There's lots of technical atomic and molecular reasons why this is, but that's only if you're going to study organic chemistry a lot closer. And so we're not really going to delve into that deeply. Instead, we're just going to give you the rules and make you be able to predict them. So because C1, 2, 3, 1, 2, 3 has more H's, it will take the H. All right, let's try it again. And so 2-chloropropane, that's the major problem. Our job is to try to look at the carbon-carbon double bond and decide which one has the more H's attached. Now, when do we have to worry about this? Whenever we have HBr or HCl. That's the only time. And it's an asymmetrical alkene. So the only time you have to worry about Markovnikov is if it's an asymmetrical alkene and the adding group has 2 different pieces to it. Okay, so clearly on that carbon, there are no H's. So the H is going to want to add here. And the Br is going to add here. So CH3, C, CH3, CH3. It's always good in my mind to write down everything else that isn't going to change. And stick a different color in. Since the H is going to go on the one with the more carbons, we're going to stick the H here, which means the Br has to go here. That's the main product. Got it? What about this one? What about the next? How do we think about this sucker? Well, doesn't this carbon in the double bond have 2 H's? And this one has 1 H? So wouldn't the H want to go onto the one with 2? And the Cl goes on the one with 1? Good. So then that's CH3, CHCl, CH2, CH3. This is one of those things that we do in organic chemistry all the time, which is, I'm not going to tell you Markovnikov. I'm not going to tell you hydrohalogen. I'm not even going to tell you anything. I'm just going to say, here's the stuff. What's the product? So it's all about identification. You have to recognize, one, that it's an alkene. 2, that it's asymmetrical. 3, that it's hydrohalogen reacting. And then you have to remember the Markovnikov rule. So that's the way you get this problem right, is you do some identification of what you have, what's going on, what the critical part is, and then what the rules are that apply. I'm not saying it's easy, it's just not. But the more practice, the easier it is to make those identifications. Cool? Cool. Can be thought of as HOH, which is very similar to HX. So it's the same sort of thing. Hydration means addition of water. And since we're splitting this up into an H and an OH, you can see where it adds. Now this isn't easy to do, so we have to have a catalyst of a strong acid that makes this happen. And so what do you make? You make an alcohol. Alkane, alkyl chain with an OH group attached. And again, a saturated product gets made because there's no multiple bonds. All right, so let's look at some hydration reactions, which are very similar to halogenation addition reactions to alkenes. If it's symmetrical, it doesn't matter, but if it's asymmetrical, it's Markovnikov again. H adds to the carbon with more H's, and OH adds to the carbon with less H's. Like gathers with like. Excellent. So it's important that if you see this, that you know and remember, okay, that this carbon has how many bonds on it right now? 1, 2, 3, 4. So it's done. It's happy. It's got its 4. How many bonds does this carbon have? 1, 2, 3. So what has to be on that? It's got a hydrogen. And because it has a hydrogen, this H will add to the one that has the hydrogen, and the OH will add to the one that does not. And so what do you get whenever you have that result? Notice how almost all of this molecule basically just sits there. It doesn't change. The ring hardly changes, all those carbons. That methyl group hanging off there, that doesn't change at all. The business end of this is the double bond CC turning into a single bond CC with an H and an OH attached. And since we decided that this H added on to that one, the H goes on here. I'm not even going to write it because well, all right, I'll write it. And then the OH goes on the other carbon, right? That's the major product. Since that carbon up there has no hydrogens, the OH adds there. This bottom carbon has one hydrogen, so the H would add there. And that's the major product coming. There it is. All right, let's see some other addition reactions. Okay, because this is symmetric alkene, it doesn't matter, right? Since that's a symmetric alkene, you're going to stick an H and an OH on there, and all you're going to make is CH3, CH2OH, which is everybody's favorite ethanol, ethyl alcohol. For those of you who are of age, that would be something that you might be doing along with burgers and hot dogs over this holiday weekend. And if you're listening to this recording on some non-holiday weekend, well, hey, it's 5 o'clock somewhere, right? It's happy hour somewhere. So anyway, that's what you're going to make there with that reaction. And it doesn't matter, because if you wrote the OH on the other side, all you'd be doing is flipping the molecule over. But I think it's clear that no, this is also symmetric. So it doesn't matter which side, right? You can stick the H and the OH, or the OH and the H, and you get the same molecule, which is CH3, CHOH, CH3. The OH is on the second carbon. If we'd have stuck the OH on this side instead, the OH would be on the second carbon. So it's the same exact molecule. All right, so what's a general summary and understanding of addition reactions? If you think about that in terms of this, I think it's obvious that this is a alkene. And what are we going to do with it? Well, we're going to do a reaction with it. If you add H2, this was the first one we thought of, you just stick a hydrogen here and here, and that's what you end up with. And that, the hydrogens look sort of funny there, but that's sort of what happens. And what do you end up making? CH3, CH3, CH2, CH3. If you're going to do X2, you get the same thing, but instead you're going to make chlorines that are attached on each carbon of the double bond. It's no longer a double bond. If you're going to then add HX, hydrohalogen, the H is going to add on to the carbon with the most hydrogens already attached. That's the key. And that's true both here and here. Follows Markovnikov. That's why the H goes at the top. And either the X or the OH goes on the bottom carbon here as written. Cool. That's a really great slide to be able to think about and predict what's going on. Okay. What are the product of this reaction? So what do you think? Well, you look and you say it's an alkene. It's asymmetrical, right? Because this carbon has a methyl and the rest, this has a hydrogen and the rest. Okay? HOH is what water is going to add onto the double bond, and you have to do Markovnikov, which means H's add to carbon with more H's. Which one of these has these carbons in the double bond has more H's? Well, this one doesn't have any, right? So the HOH, the H is going to add here, and the OH is going to add here. So which one ends up doing that? I also strongly suggest that rather than get mesmerized by the possible right answers, you spend a little time, you go ahead, go through the business, and write out what you think the proper product is, because if you do it right, the answer is waiting for you. That's it. There you go. That's the stuff. Now let's talk briefly about polymers, just because you may be getting polymerization going on in one of your labs that you might be doing next week. So let's add this in real quick. The reason why we're going to talk about polymers isn't about what they are, but how they're made. And the reason why that's important as far as alkenes and alkynes are, polymers are poly, meaning many, connections of little pieces of monomers. Mono means one. So a single piece is a monomer, and whenever we connect a bunch of monomers, we make a polymer. Okay, so monomers are covalently bonded to form the polymer, so they attach. And the way that you put these together often are with these double bonds. We take a bunch of these ethylene monomers, ethyl meaning two carbon, ene meaning double bond, and whenever you connect a bunch of them together, notice that there's no double bonds because you connect them such that the double bond disappears. You have a polyethylene polymer. So polymerization is just the joining together of monomers to make polymers. There's polyethylene, so ethylene is the monomer. Polyvinyl chloride, so vinyl chloride is the monomer. Polypropylene, So propylene is the monomer. Polytetrafluoroethylene, so tetrafluoroethylene is the monomer, and you stick a bunch of them together. The double bond disappears, and that's how they connect. Dichloroethylene is the monomer. Styrene is the monomer. And you can see that. There it is, and that's where it comes from. Saran wrap is this stuff. PVC for PVC pipe. Or garden hose is there. There's the polyethylene, PE. For bottles, polypropylene, that's the synthetic fiber for some t-shirts. Polystyrene, styrofoam, polytetrafluoroethylene for Teflon, tetrafluoro. Okay, so those are some of the ones that you've seen before. And here's some synthetic polymers, ethylene, and you can see that that's the monomer unit in which the double bonds get connected to the next thing. That is very similar, but it's got a chlorine instead of all hydrogens, and those connect by breaking the double bond and making carbon-carbon single bonds instead. You can see that carbon-carbon-carbon, that's 3, that's propyl. So they connect. Tetrafluoroethylene, so it's like an ethylene, except instead of hydrogens, it's got nothing but fluorines. Dichloroethene connects. They don't have a special fun word, so they just call it saran wrap. And there's styrene, which is phenylethene, and polystyrene. So that's how those guys work. And all of them come from monomers that contain an alkene or something similar. Carbon-carbon double bond.